All right, folks. Thank you for joining me again for this example on how you can design a controller for your plant so that you can achieve the desired response. Okay, so hopefully by now you would have obtained your plant in a single transfer function form for your projects like we have discussed in the previous videos, and hopefully they are matching your original block diagram that you created in Simulink. Okay, so if you have those two pieces working, so you can actually move on to the controller design as following the approach I discuss here. Okay, so this is basically an example. It might not be even close to what you have, but we're going to use an example or a toy example here that we can use to elaborate the same concepts that you're going to be using for your project. Okay, so you're given a plant or you have a plant, and then the next couple of pieces of information you need to know what kind of a controller to design, and then what are the desired response. Okay, what's the desired response you expect to see. So here typically, if you want a zero steady state error, you will need to have some form of an integral control, and then we will be talking about this down the road. But given the example, I specify you to design a PI controller, and then the selection of the PI controller or why it's a PI controller is not part of this discussion today, but you will be selecting a PI controller or a different controller, and we'll learn about the concepts associated with that process later. Now here you are expected to use a PI controller so that you get zero steady state error. And then the second is you are provided a characteristic response, or your final controlled response should have a response that's similar to a second order response that has the following poles in the S-plane. Okay, now you don't have to have it in the form of poles. You might be given percent overshoot and settling time, percent overshoot and peak time. So using those pieces of information and the theory that we learned in our previous lectures, you should be able to come up with a second order response or second order characteristic that defines, or that can be described based on poles in the S-plane. Okay, so in this case I've simplified that process for you and I've given you the poles, but in the case of your project you will need to come up with these poles given the desired response I have provided. Okay, so keep that in mind. All right, so now you are provided these desired responses, and then we are saying, okay, we need to design a PI controller. So let's sketch out the overall block diagram. Okay, so when we sketch out the block diagram, we can see this is our PI controller, right? This is our plant. Okay, this is the plant, this is the PI controller, and then this is, let's say this is our output and this is our input, and we have a unity feedback system. Okay, unity feedback system. Now for some of you I have provided a feedback gain. So this is your feedback. Okay, this is your feedback, and there might be a gain of some sort, okay, associated with this. So let's call this gain K sense. Okay, so sense again, K sense. So if there is such a gain, you will need to consider that as a part of your design. You'll need to consider that as a part of your design. So make sure you include that in your root locus plot. Okay, so I'm not gonna get into that right now, but you do need to remember to include this for your design. Okay, all right, so let's take a look at our controller for a little bit here, because this has some unique properties. Okay, so Kp plus Ki over S, so this is the proportional gain and this is the integral gain. That's operating on the error. This is the reference, this is your feedback, so this is basically your error. And if we simplify this, we have kps plus ki over s, and inherently we can see there's a 1 over s term that helps drive the steady state error to 0. Okay, all right. And then when we simplify this to a gain, which is kp, a constant, times this is a 0. Okay, this is a 0 in the numerator, so the value, the function is in the numerator, so therefore this is a 0. All right, and that's governed by the pole location s equals negative ki over kp value. Okay, this we don't know yet. That's part of the design. And then of course we don't know the kp value, which is our gain term in that forward path, right? Or gain that's in the controller. So those are the two elements that you will need to design in the process. Okay, so how do we approach this? Let's see what we do here. So the first step, okay, the first step is we're gonna sketch out our closed loop system. Okay, closed loop system, and then we're gonna look at what we already know, because if you look at your controller, right, we are introducing this 1 over s term, right? You can't change that. Okay, you can't change that. It is where it is, right? It is where it is. So you can actually include this in your first analysis. Okay, how do we analyze? We use the root locus. Okay, we use the root locus, and ultimately what we are looking at is, once we plot the root locus, we are going to see how far are we from these poles that describes the desired system. Pay attention. How far the root locus is from the poles that describes the desired system, right? Because as soon as these poles are on the root locus, now we can choose the gain k, or in this case kp, so that you achieve that desired characteristics, right, with the feedback loop. But in order for us to evaluate this, we will need to first look at the system along with anything that is fixed, because this is fixed. We can't change anything. There's no ki, there's no kp, nothing. We can't move it, right? So now we take into account elements that are fixed, and we look at the root locus and see, with respect to our desired characteristics, where the root locus is at. So that should be your first step. Okay, so in this case we're going to set gc to be k over s. K is actually the variable, right? So when you plot the root locus, you're gonna basically use so we need the open loop path, open loop characteristic equation, right? So then that's going to be, so let's say open loop transfer function, that's going to be 1 over s times 10 over s plus 5 s plus 60. Okay, and if you had a feedback path gain, that also needs to be accounted for. Okay, k sense, and it should be a value, not a variable. All right, and then we don't account for the k or the kp at this time. In this case, in our case, k is equal to kp, the way we have set up our controller. And we don't usually place this, or you don't usually include this in the root locus, because MATLAB takes care of that automatically. Okay, it automatically takes care of that. So this is the open loop transfer function that we are going to use. In my case, this is 1. Okay, in my case, this is 1 because there's no feedback gain. So let's see what this root locus looks like, and then we can try to plot our desired characteristic poles, or desired system poles on the root locus and see where we are at. Okay, and then we can decide what to do next. Okay, so let's see what that looks like. So I'm gonna switch to my code here. So here I have set up the transfer function. First 10 over s plus 5, I basically separated these two to one transfer function because they are a product. And then I multiplied that with 1 over s plus 60 times 1 over s, right? So these three are multiplied, and then I'm performing a root locus. And then I'm gonna, first let's look at the root locus. Okay, so let's see what that looks like. So when we click the run button, we should see the follow. Oops, let's run it again. There we go. Okay, so this is our root locus. Okay, you can see that if you zoom in a little bit, right? So we have our 3 poles, right? One at 60, one at 5, one at -5, -60, and one at 0. So good, we have what we need. And let's add the desired locations, okay? Because they should be somewhere around here, right? So there should be one here and one here. So let's see once we add those what that looks like. Okay, so we're gonna just uncomment here. Run it. Okay, so those are the desired final controlled system or location, right, to get that desired response. So they are nowhere close to where we want because our root locus is going this way. So far it's not looking good, right? But keep in mind, we still have something in our hands that we can use, right? Which is the 0, right? Oops, which is our 0 here. Okay, so we have a 0 that we can use to our advantage, right? So we know that zeros contribute positive angle, right, to our root locus, contributes positive angle. Now when we look at our root locus here, what we need to do is we need to calculate with respect to this point, right? Because if the root locus goes through here, our total angle contributions at that point should be 180, right? So we have to find out how much angle is evaluated or can be evaluated with respect to this point, and then how much of a deficiency is there when with respect to that specific point, with respect to the desired point. Okay, so the way we approach this is we look at our S-plane. Okay, so this is our S-plane, this is our root locus plot. We have a pole at 0, we have a pole at -5, and we have a pole at -60. Okay, and then we have the desired response characteristics at 20 and -20, right? And this might not be round numbers for you, but in this case they are. So what we do is we choose one. We're going to choose one, and then we're going to find the total angle contribution by the poles that we have already with respect to that point. So we call this θ1, call this θ2, we call this θ3. Okay, so so if we can find these angles, then we can calculate what's the total angle contribution. So I'm sorry, guys are not seeing that. Yeah, okay, here we go. Okay, so you can now calculate θ1, θ2, and θ3, right? So with respect to this point, which means, or which describes the total angle contribution from the poles, okay, from the poles. And so let's do that right now. So if you look at this angle, I believe, let's see, And we know these are all poles, right? And we know poles add negative angle and zeros add positive angle, poles negative angle. Okay, so basically our total angle in this case, okay, total angle at the desired, with respect to the desired pole location, one of the pole locations, you don't have to calculate for both. The total angle is negative theta 1, negative theta 2, negative theta 3. Okay, negative theta 1, negative theta 2, and negative theta 3. Then how do we find these values, right? So in order to find theta 1, we know this is 40, we know this is 20, right? So that angle is tan inverse 20 over 40, right? 20 over 40. So this is around 26.56 degrees. So likewise, you can calculate all three angles, okay? And if you do that, you should get negative 26.56 degrees, negative 126.87 degrees, and 135 degrees, right? This is 126, this is 135. So when you sum them all up, we should get negative 288.43 degrees. Okay, so that's the total angle contribution from the poles considering this point in the S-plane. Okay, now how is this useful? Let's think about that, right? How is this useful? Because this tells us this is the angle, amount of angle that with respect to this, that these poles contribute. Okay, so if that's the case, let's talk about angle deficiency. Angle deficiency tells you how much angle, how much of an angle are we short of for us to meet the angle criteria of the root locus, meaning how much angle do we need to contribute with our zero to counteract some of this angle to bring this total angle to 180, because that way we can allow, or we can help the root locus go through these points. Okay, so let's calculate angle deficiency. So we call that angle deficiency. Okay? So angle deficiency is nothing but the total angle plus 180 degrees. Okay, because that's where we want to be, at 180 degrees. So negative 288.43 degrees plus 180 degrees gives us what? So 8.43 plus 180, so that's 108.43. Okay, so 108.43 degrees, and I believe that's negative, right? So that's negative. So that's the deficiency. That's how we are deficit. That's the amount of deficit we have. Okay, so now if we can contribute from the zero, using the zero of our controller, which we have available, z plus ki over kp, right? S plus, I'm sorry, S plus, that's controller again, right? Let's make sure, ci over kp, that's right. So if we can add this amount of angle using this zero, right? Now our poles and zeros combined with respect to that desired pole location, right? Poles and zeros combined with respect to this, meets the angle criteria of the root locus, meaning root locus is going to pass through that point. Okay. Okay. So then, since this is a deficiency, the angle contributed by the zero has to be positive. Okay. So therefore, the zero must contribute 108.43 degrees. Okay, 108.43 degrees. So given the needed angle with respect to a certain point in S-plane, how do we find where the zero should be? Okay, so let's think about that. So we know our desired pole, let's choose just one of them, right, is at 20 and negative 20. Okay, and we need an angle of positive 108. So our zero should be somewhere here between these two, right? That's when you have an angle larger than 90, which is 108. So if this is here, let's call this negative B. Okay, so let's call that point negative B. You can call it negative, I mean, you can call it negative A if you want, but negative B, let's choose that. And then if that's the case, then if we can calculate this angle, or if we can calculate B such that this angle is 108.43, now we can see if that helps our controller response. Okay, so how do we do that calculation? This is how we do it. This actually, for some of you, it might be quite straightforward now, since we know where it is, right? We can write an expression 180, let's go to a new page, 180 degrees minus tan inverse, okay, so 180, this is 180, right, minus tan inverse, we're going to try to find this angle, okay, which is nothing but tan inverse, what is it, 20, right, 20 minus 20 by 20 minus b, right, 20 minus b, because this is 20 minus b, right, magnitude wise 20 minus b. So if you calculate that angle, then we can associate that to the angle that we're trying to set. So 180 minus this angle should equal to 108.43, right? Tan inverse 20 over 20 minus b should equal to 108.43 degrees. Okay, so then if you do the math here, you'll get that 20 over 20 minus b is equal to 3.0009. Okay, therefore solving for b, we get a value of 13.33. Okay, 13.33, meaning our zero is going to be at negative b, which is negative 13.33. Okay, that's the zero location, negative 13.33. Okay, so let's see what happens in this case. Okay, so we're going to go to our code here, and then we're going to create or update our transfer function. Yeah, let's, I can't find the uncomment button, there should be one. There we go. Oops. So we come here, and then so we have the same system. And copy all this again. Then at the very end, we have some flexibility to add a zero. That's our zero term. Okay, and that's gonna be, what did we say? It's gonna be 13.33, right? 13.33. 33, and there's nothing in the denominator because the denominator is basically 1. Okay, so that's set to 1. And then we're going to plot this in a new figure, new root locus, right, of the new system with the controller. 60 and then 1, 0. We have the S term, we have everything, we have the 0. And then again, we're going to plot our desired system poles. Okay, so first of all, actually, let's try without them. Okay, have something, right? Let's try with those locations. Okay, voila. Okay, so now you can clearly see our design was good. Design is correct, right? So the root locus goes right through those desired pole locations. Okay, goes right through them. All right, so let's come back to our diagram here, right? So if we look at our root locus, or at least let's look at our controller, right? So when we look at our controller, we have defined this term, right? We've defined this to be S plus 13.33 over S. So that's defined, okay? What's left is the KP value, right? KP value. So for us to design that or decide that KP value, that's basically a gain, right? So if we go into this root locus, okay, if you go into this root locus up here, and then if you measure, if you use a data tip and measure this value, you will see that the gain is 150. So in order for us to reach the desired location, our KP should be set to 150. All right. So now we know two pieces of information. We know KI over KP should be 13.33 and KP should be 150, right? So therefore now we can find KI, which is KP times 13.33, which is 1999.5. Okay, so there we go. Now we have designed the PI controller that gives us, or that makes this system reach these two pole locations, which gives rise to the desired response, the response that we want, which is achieved at those 2 points. Okay, all right, so hopefully all of you can follow this, okay, and try this yourself. First of all, try it with this example, see if it works for you, and if it does work for you, that's great. You can move on to your projects. If it doesn't work for you, first check with me and find out if you have made any mistakes. Otherwise, I think all of you should be able to get this to work like this, and then you can implement this in Simulink, your controller, in the form of, you know, those KP and KI values in your original block diagram, and your closed loop response should match. Okay, closed loop response should match, and when you inject a transient, a load change, your response again should match and still have 0 steady state error. All right, because that's what we designed the system for. All right, okay, I know it was a little bit of a lengthy video this time, but I hope it'll get you through the project design phase, and let me know if you have any questions. Thank you.